name is Ashwin Srinath. I'm a senior software engineer at NVIDIA. I'm going to talk to you about a project we've been working on called cudf.pandas, which is a tool that lets you take pandas code and run it on the GPU without making any changes to it. To give you an outline for this talk, we'll start by doing some reflection on pandas and some of the alternatives to pandas that have come up over the last couple of years. I'll give you then a demo of cudf.pandas and show you what it's all about. Then we'll come back and talk about how it works, some frequently asked questions and some limitations, and then we'll conclude. The demo that I'm going to use for this code, you can access using the QR code on the top right. You can also find it as the latest updated repository on my GitHub. My GitHub ID is SHWINA. But we'll come back to that QR code in a bit. Okay, so I want to talk about pandas, and I want to talk about some of the other kind of alternatives to pandas. Pandas is great, but it can be slow. On the right, you're seeing the results of the H2O AI benchmarks that are maintained by duckdb, and it's measuring the amount of time it takes different libraries to do a group by on a 5 GB dataset. And you can see here that pandas appears near the bottom of this benchmark in terms of performance. So why is pandas slow? It's for two reasons. The first is that pandas is largely single-threaded, which means that it can't use more than one CPU core on your machine. And it's not a query engine like a lot of these frameworks and libraries are. So there have been a lot of alternatives to pandas that have come up that try to address the performance gap. Some of these are written in a faster underlying language like C++ or Rust. Some of these are more SQL-like. They don't have a pandas-like API. Some of these are query engines. Others let you distribute your computation across computers. And some of them are hardware accelerated, or they can use things like GPUs. So I want to talk about cudf, which is a GPU-based data frame library. It's the project that I work on. It's a library in Python that gives you a pandas-like API, except that it runs on GPU. Underneath, cudf is written using a combination of CUDA, which is NVIDIA's programming language for talking to the GPU, and C++. And that underlying library is called libcudf. And because libcudf can work with the GPU, and because GPUs are fast, cudf is extremely fast. It can be up to 10 to 100 times faster than pandas, depending on the operation you're doing. You can see here on the lower right some of the speedups we get versus pandas for different kinds of operations you might want to do with pandas data frames. cudf supports about 60 to 75% of the pandas API, depending on your definition of the pandas API and how you measure it. So it doesn't support all of pandas. But we're not going to talk about cudf in this talk. We're going to talk about something else. We're going to talk about how to take your existing pandas code and not have to import anything, not even cudf, and just be able to run it on GPUs. We'll talk about what that gets us and all the nice things about it. So just stepping back and asking this question, if I'm a data scientist or I'm a library developer that works on a library that uses pandas, should I switch from pandas to something else? And the answer is maybe. There are reasons to use something other than pandas, like polars or Dask or even cudf. And there's reasons you may not want to use those libraries. Some reasons you might want to switch away from pandas is if performance matters to you a lot. If performance matters to you a lot and you don't mind rewriting your code, for example, then you should switch away from pandas because there are definitely faster alternatives. If data size is what's limiting you, if you have terabytes of data, for example, then pandas is unwieldy at this data size. So you might want to use something else. But there are reasons you might want to keep using pandas. For example, if you like the API flexibility that pandas gives you, then you'll see that some of these alternatives don't really have the same amount of flexibility in their APIs. If you're collaborating with people that use pandas, then you may want to stick to using pandas. Another big reason to use pandas, especially if you're a library developer, for example, is that pandas is very battle tested. There's a huge ecosystem of libraries that are built on top of pandas, and we're not going to have an easy time convincing the maintainers of all those libraries to switch away from pandas into something else. And then the final and maybe the most important reason that you might want to keep using pandas is that it is getting faster. There's been a few talks at PyData Global about some updates that have happened to pandas, or explaining those updates. We've seen some nice speedups between pandas 1 and 2, and we're going to expect to see some more exciting speedups between pandas 2 and 3. So pandas is getting faster. So I'm now going to talk about cudf.pandas and what we're trying to achieve with this project. cudf.pandas is exploring what it might look like for everyone to say, okay, I'm going to keep using pandas, but I also am going to get the speedups that I can get from using the GPU. So how does this work? It lets you keep using pandas. You don't change anything about your code. You still import pandas in your programs. You still use libraries that use pandas. But those pandas calls are accelerated on the GPU. And cudf.pandas can in this way support 100% of the pandas API. The way it does that is that certain operations run on the GPU and other unsupported operations run using pandas on the CPU. Third-party code that you might be using is accelerated. No one needs to change their code, but everyone gets to use the GPU without any changes. How does this look? It looks like what you're seeing on the right here. If you're running on Jupyter, you just load an extension called cudf.pandas, and now pandas calls will use the GPU. And there's similar incantations for when you're using the command line, or if you want to directly import the cudf.pandas extension and install it. So at this point, I'm going to switch to a Jupyter notebook, and I'm actually going to show you what this looks like, what the experience is using cudf.pandas. There's really not much to teach here. cudf.pandas just lets you use pandas like regular. There's no new API to learn, but I'm going to show you some kind of tricks to get better performance and show you some neat features of cudf.pandas. You're looking at my Jupyter setup here, which can be a little intimidating to look at, but I'll explain what's going on. We're basically going to run a single notebook. There's two versions of that notebook. On the left is the version that we're actually going to run here. And that version of the notebook loads the cudf.pandas extension. There's a copy of this notebook on the top right that just comments out that line, which means that when we import pandas on the left, we're going to import cudf.pandas version of pandas. And on the top right, we're going to keep using regular pandas. I've also given the kind of pure pandas notebook a head start here, and I've gone ahead and executed all of the cells, just because it can take some time. But the cudf.pandas version, we're going to run live and see what that looks like. And on the bottom right here of the Jupyter screen, you'll just see the two GPUs that I have on my machine and what's going on with them. OK, so let's see what we're doing. In the first part of this notebook, I'm just loading the cudf.pandas extension. I'm importing a few Python libraries. I'm generating some random data. And then I'm going to apply some very common kind of pandas operations on that data. If you look at the results that I got on the CPU, you'll see that I timed those results. And we're going to compare those timings with what we get when we use the GPU via cudf.pandas. So for this group by operation, for example, on the CPU, it took about 160 milliseconds. On the GPU, it takes about 1/10 of that. OK, what about when we do a string operation? I'm looking at a string column, and I'm trying to see if it contains another substring. On the CPU, that took about 3 seconds. And with the GPU enabled, it takes 50 milliseconds. OK, a couple more examples here. Well, I ran the wrong code. The string contains is actually 9 milliseconds on the GPU. I went ahead and ran the second example, which is a merge, which on the CPU took 1 second, and the GPU was 50 milliseconds. And then this last one's interesting. We're doing a count operation on both the axes of the data frame. And what's interesting about it is that when we run count, the count method on the 0th axis, that is actually quite fast on the GPU. But when we run count on axis equals 1, which is along the rows, that's actually slower than the pandas version. The pandas version took a little over a second, and the GPU version using cudf.pandas takes closer to 2 seconds. OK, so we saw some impressive speedups from using the GPU for relatively simple operations. But we also saw one example of where we didn't get a speedup. So how is this working? How are we actually getting any kind of speedup from using pandas operations when we load the cudf.pandas extension? Well, it happens because when you load the cudf.pandas extension and you import pandas or any of its submodules, what you get back is not the actual pandas library. You get a proxy for the pandas library. That proxy contains proxy functions and proxy types, and those types have proxy methods. And the way these proxies work is that whenever you invoke one of these proxy functions or methods, what actually happens is that you are invoking a function that's going to try to execute the cudf or GPU version of that function first. And if that fails for some reason, it's going to copy data from the GPU to CPU and then execute the pandas or the CPU version of that function. And then we return a result back to you. But all of this happens behind the scenes. And to you, the end user, it really just looks like you're using pandas and things just magically happen on the GPU. So this kind of explains why when we ran the count method and we provide access equals 1, that ran slower than regular pandas because we not only had to, well, that not only fell back to using pandas on the CPU, we also had to pay the additional cost of moving data between the CPU and the GPU. And that can be significant when you have large data sets. Okay, so moving on. When we use this proxy library, cudf.pandas, can we continue to use third-party libraries like Seaborn? The answer is yes. I'm plotting my data. Remember, my data lives on the GPU at this point. I'm plotting some data in my data frame by passing it to Seaborn, and it just works. It just works because Seaborn is also importing pandas, but when it does that, it's also importing this kind of proxy version of pandas, and everything just works smoothly with each other. Okay, so we're moving on now to the second part of this demo. We saw some basics of cudf.pandas, how to use it, and some of its essential features. But I want to talk more about this question of performance. We saw that we got some nice speedups from using cudf.pandas, but we also saw that there are situations where your code may not get a lot of speed up. And in fact, you might even get slowdowns. So I'm going to talk about what you can do about that. To study this problem, we are going to generate some time series data, and we're going to do some operations on that data. Specifically, we'll generate the data, and then we'll filter it to just the data that includes data for timestamps between 9:30 a.m. and 4 p.m. And then we'll do a group by on the resulting filtered data. So I'm running this with cudf.pandas on the GPU. You'll see some activity here on the lower right. And you'll see that this is taking some time. It takes some time even on the CPU. I'm showing you on the CPU, it took about 11 seconds. And we'll see that on the GPU, it took 13 seconds. So we're not seeing very impressive numbers here from utilizing the GPU. So cudf.pandas comes with tools for you to see if you can solve this problem. What it comes with is a profiler that you can enable in the notebook with the magic cudf.pandas.profile. So I'm just running the same code with the profiler enabled. And we'll see what that looks like in just a few seconds. Okay, so the code runs like before, but now we also get this report that tells us every pandas function that was executed. So you can see that these are the names of different pandas functions and methods. And also it tells us whether those functions executed on the GPU or on the CPU and how much time they took. And what you'll notice here is in this code snippet, everything runs on the GPU except this one function, indexer between time. So looking back at our code, this one function is what ran on the CPU, everything else in this cell ran on the GPU. And it can sometimes happen that when you have bottlenecks like this that run on the CPU, that can slow down your code in a significant way. The key to getting really good performance with cudf.pandas is to minimize the number of times this happens. You really want to fall back to using pandas or the CPU as little as possible. So one way to do that is to basically rewrite your code to use functionality that's supported by cudf or on the GPU. And I'm doing that here by replacing the call to indexer between time using pandas supported datetime properties. So instead of the call to indexer between time, I'm using the .hour and the .minute datetime properties. And we'll see that that gives us the same results, but it's also much faster. Where previously on the GPU we took 14 seconds, we're now taking less than a second, about 700 milliseconds. Now, here's the really cool thing. When you rewrite your code in such a way that it can execute efficiently on the GPU, it ends up that that code actually runs faster on the CPU or using just pure pandas as well. On the right here, I've shown you the result of taking this modified GPU optimized code, and I'm running it using the regular pandas. You'll see that we've brought the execution time down from 11 seconds to 6 seconds. So a nice kind of 2x speed up. So often this is like a win-win. The more efficiently you write your code for the GPU, the more efficiently it will run using regular pandas as well. Okay, and then I'm now gonna move over to the last part of my demo, which is showing how cudf.pandas not only accelerates the code that you write, but it also accelerates the libraries that you use. For this example, I'm using LangChain because it's new and exciting. But the point isn't to show off LangChain or its features or LLMs or any of that stuff. It's really to show that we can take this library that was written to use pandas. It was written without cudf or GPUs in mind, and we can make it auto-magically use the GPU. And that can be to our benefit. We can get some nice speedups from using those libraries. There's a lot of caveats to this. Setting up this example is kind of finicky. Please make sure if you're trying to reproduce this that you read the notes that I have here. But I'm kind of gonna just gloss over the details and walk you through what's going on. So at the beginning of this, I'm going to import LangChain, and I'm gonna set it up. I'm going to then load some data into a data frame using the read parquet function. When I do this, you'll see that my GPU kind of fills up on the bottom right. Okay, so we've loaded our data. I've then kind of filtered out to just the columns that we're interested in. The data set that we're looking at is the New York City taxi data set. It contains information about taxi rides in New York, including like pickup and drop off date times, the company that owned the taxis for each ride, how many passengers there were, how much did they tip, and whatnot. We're then going to create a LangChain agent, which will help us ask questions about this data. And it will answer those questions by executing pandas code for us. So we don't actually have to write the pandas code to answer these questions. So the first question I'm asking is, how many rows are there in this data set? And you can see that it answers with, there's about 30 million rows in this data set. I'm asking another question, which is, which company received the most tips out of this data set? And you can see that it very quickly answers that too. The final question that I'm asking is a little bit more complex, and it's going to need pandas to run resample operations. And those can be sometimes slow with pandas. So when I ran this example with pure pandas, you can see on the top right, this question took about a minute to come back to me with an answer. And we'll see that because we're using the cudf.pandas extension, LangChain will actually end up using the GPU for this query. You can see there's some GPU activity. It completes very quickly, and we get the same answers, except we got it in 2 seconds instead of a minute. So again, the goal here wasn't to show off LangChain's pandas integration. It's really to show that a library that was written without the GPU in mind can still use the GPU because of the way cudf.pandas works. Okay, so just to do a recap of that demo, cudf.pandas accelerates your code on GPUs with requiring no changes on your part. The key to getting good performance from cudf.pandas is to minimize the CPU execution. And third-party libraries that are written to use pandas can now use the GPU via cudf.pandas. Okay, let me switch to full screen here. So how does this work? What is actually going on here? It works by a couple of kind of tricky bits of Python. The first is it works via proxy pattern. We have proxy types and proxy functions, and those proxy types look something like this. We have our own version of data frame, and every method of data frame, for example, count, works like this. It tries to do the operation by calling the underlying cudf count method. And if that fails, it's going to kind of orchestrate the movement of data between CPU and GPU, and it's going to run the pandas version of that method. And we have some tricks to kind of auto-generate these proxy types and proxy methods for us. The second trick is that we have to customize the way import works in Python. So when you do import pandas with the cudf.pandas extension loaded, we have to deliver a proxy module to you. We do that by using some of the kind of more advanced tools provided by the Python standard library and the import lib module to hack the way imports works. Does this really work? It does. We test directly against the pandas test suite, and currently cudf.pandas passes 94% of the pandas test suite. So that's the degree of compatibility you can expect between using kind of regular pandas and cudf.pandas. But what about some other approaches or other projects in this space? What about duck typing? A lot of existing pandas-like libraries expect to work with the world using duck typing. But duck typing doesn't always work. It doesn't work for free functions like pd.readcsv. So you can take some data frame like object, and you can pass it to some function expecting a pandas data frame, and that might work. But what if this function is calling free functions like pd.concat or pd.readcsv? At that point, things start to break. The other thing is that there's a lot of code out there that is currently doing hard is-instance checks, which means that you can try to pass in a pandas-like object, but it will still fail because a lot of code out there is saying, I'm expecting a pandas data frame by doing an is-instance check. So duck typing is great, but it doesn't always work. There's also another effort that we should talk about here, which is the data frame standard API. This is maintainers of different data frame projects coming together and deciding on a standard API for data frames. And that kind of solves some of the problems, but it's still solving a different problem than the one we're trying to solve. We are trying to enable the pandas API on GPUs, but the data frame standard API is more a developer-focused API. So if you're a library developer, then it is appealing to use the data frame standard API. In fact, we are excited about the data API. We're part of the consortium. We are working towards developing the standard with other data frame maintainers because it's going to unlock some exciting possibilities. Like it's going to enable us to fall back to a faster data frame library like polars when it executes on the CPU. Okay, so I'm going to end this with some FAQs. The first one is, will my code run 100 times faster? The answer is yes. If you write your code using idiomatic pandas or using parts of the pandas API that are meant to be efficient for data processing, you can get really good speedups using the GPU. And the profiler will help guide you here. It will show you what parts of your code are running efficiently and what parts are running on the CPU. As a bonus, if you optimize your code for GPUs, you'll get better CPU performance. Second question, how much of the pandas API does this support? We really do support 100%. Just remember that some operations fall back to the CPU. Will cudf.pandas work with some arbitrary third-party library? Yes, but with some known limitations. If there's hard is-instance checks for NumPy arrays, that does work. Libraries that use the C API or subclass pandas.dataframe are known not to work. We're working on resolving these issues, but right now you can expect some rough edges. And finally, what about working with data that's larger than GPU memory? Again, this is a problem that we're actively thinking about, but right now, this will work. It will just work by falling back to the CPU. Okay, so how do you get started? Again, there's a QR code on the screen for accessing the materials from this demo. There's some resources in that GitHub repository that will point you to places like the cudf.pandas docs. There's also a link to try this on Google Colab using a free GPU instance if you don't have a GPU handy right now. With that, thank you, and I'll see you all on Discord to answer questions. And if we have some time, answer some questions here.
Fantastic. Thanks so much, Ashwin. That was phenomenal. It looks like we have a few questions in the chat. We got 5 minutes, so we'll kind of hit as many as we can. And obviously, everyone in the audience, if you have any lingering or pending questions, feel free to toss them in the Q&A. We can get them answered to you, hopefully, before taking this to Discord. But let's open up this chat real quick. So we'll have them collateral.
Do you want me to go ahead and pick these and answer something? Or I'll let you coordinate. Sorry.
No, yeah, of course. I said we can jump into it. So this first one I see, do we get improvement in performance only when we use cudf.pandas on GPU, or are we also getting performance gain on the CPU as well? Also, does it work in cluster, example, multi-nodes architect?
Okay, these are good questions. So cudf.pandas really is a GPU accelerator. If you're on the CPU, you're just using pandas, so there's no speed up. And if you have a GPU, it's going to accelerate some functions on the GPU. So it's not going to rewrite any like CPU code for you. So you only get speed ups with GPU. The second part of this question is, can you scale this to multi-nodes? cudf.pandas, we have some initial tests to show that it's working with Dask. It's going to be something that we spend more resources on. And scaling it out with Dask is one option, although there's going to be a few more options for scaling out in the coming months.
Awesome. It looks like, are there Docker images available? Otherwise, I imagine this is difficult to install in environments without Conda.
Yep. So we have Conda, pip, and Docker install instructions. I think the best way to find them is to get to our GitHub repository. Just search for GitHub QDF or go to rapids.ai, and you'll find yourself in the install page for different Rapids libraries, and you can find the instructions for all of those platforms.
Awesome. Looks like there's some questions around where to find this material. So again, we'll take this to Discord. There is a landing page within the reception area, within the Air Meet, where you can kind of go in and play around with some Discord for different talks that we've had so far. There was a question: is there a problem with GitHub link or QR code?
Maybe. I'm gonna make sure that this GitHub repository is public. But I will post an update to Discord and make sure everyone can access this.
Awesome. So it looks like it's not working currently. For applying UDF, will you have benefits using the GPU?
Yes, we actually take user-defined functions and we compile them with number. So if you're operating on kind of more common data types like numerical types or date times or even strings, those will actually execute on the GPU. There's some limitations here. There's a whole page in the QDF docs that explains the limitations and capabilities of user-defined functions.
Phenomenal. That's everything thus far. Again, we got about 2 minutes left. So if there's any pending questions, feel free to drop them in here real quick. Again, I just want to say quickly thank you to all the attendees who chose to take some time out of their day to attend this talk. Obviously, Ashwin, thank you so much for going in depth in this presentation and demo. I found it to be super, super useful. So like I said, if there's no pending questions, I'll give you guys maybe a few minutes or a minute to navigate to your next event. But it looks like demo is going.
Okay, so sorry. The issue here was that this was private, and I'm going to make it public just now.
Do you want to toss up the QR code real quick, just in case people, as they're away out the door, want to scan?
Yep. The QR code will take you to the URL, but I'll also post it on Discord, and it's going to work in just a couple of minutes when I make this public. I apologize for the confusion.